All right, next round of angles. So double angle identities. We actually went over the first two, cosine and sine. Again, you can memorize these, or you could use the composites where you're taking 2 theta and writing it as theta plus theta, or 2x and writing it as x plus x. Do keep in mind on that cosine of 2 theta, you could then use that Pythagorean Papa Pid and sub in for either cosine or sine squared on another step if needed. So we're going straight into verifications. So verifying the identity, again, from the last round, always look at the angles. The more complicated angle, work on it. They've got to match. So I've got to take 3x all the way down to x. So if I'm looking at this one, let's see, 3x would be 2x plus x. Whoa, where'd it go? Oh, that's weird. Let's try that again. 6.3. Okay, it's back. That was fun. Doesn't want me to do it. Cosine of 3x, so we're going, I'll just write them up here. 2x plus x is what we're going to view it as. So composite for cosine first. Cosine's selfish, likes to go with itself. Cosine 2x, cosine x, opposite operation, sine 2x, cosine x. I'm sorry, sine x, sine. All right. From here, double angle on cosine. So I'm not going to use the composite now that we've covered the actual double angle itself. The double angle for cosine is cosine squared minus sine squared. So that went in for the pink, so I'm going to put it in a pink set of parentheses. This cosine is still sitting here. And then your composite for sine 2x, we'll put it in a purple box, is 2 sine x cosine x. So again, I'll put it in parentheses. And I don't think I have room to write that last sign, so scoochy, sine x. All right, so that everything's down to 1x, so now I'm going to distribute that cosine. That's going to give us cosine cubed minus cosine times sine squared. All of this back is one chunk, so minus 2 cosine sine squared, because there's 2 sines in there. And let's see, if we look at this, I've got to get it down to 3. I've got the cosine cubed, but I'm supposed to have 4 of them. So let's go with, I'm looking at the other side. I do not see a sine squared anywhere, so I'm going to sub in Papa Pid for both of those sine squareds. So now we're subbing in. I need some more color. Let's change colors. And the winner's green. All right, so we're going to sub in Papa Pid on both of these, here and here, because the other side doesn't have sine squared anywhere, so I need to make sine squared go away. All right, so we've got cosine cubed of x minus cosine x, and then that sine squared, Papa Pid, 1 minus cosine squared. And then we've got minus 2 cosine x, and then again, Papa Pid it, 1 minus cosine squared. And we do some more distributing. So cosine cubed minus distributed cosine x, because it's multiplied by 1. Negative times negative is a positive cosine cubed. And then distributing negative 2 cosine times 1, negative 2 cosine. Negative times negative, positive 2 cosine cubed. All right, we get a lot of cosine cubes. 1, 2, 3, 4 cosine cubes. So combining like terms. And then negative cosine and a negative 2 cosine would be a negative 3 cosine. And I think that's what we wanted. Power reducing identities. So the power reducing identities are useful if you've got a power of sine cosine or tangent, and you need to get it down to a single power of something. Also, make note of the angle. The angle was a singular angle. The price of using it is to double the angle. All right, example 2, use power reducing identities to express the given expression using a single power of cosine. So single power of cosine. So cosine squared is not going to work, so we're going to use power reducing on both of them. So sine squared of x is 1 minus cosine of 2x over 2. Sine squared, 1 minus cosine of 2x over 2. Times cosine squared, cosine always goes and adds to itself, back to being selfish. 1 plus cosine of 2x all over 2. Right? Cosine add to itself, sine subtract. So top times top, bottom times bottom. Denominator is going to be a 4. Difference of squares, 1 times 1. Outside, inside drops, minus cosine squared of 2x. 1 minus cosine squared of 2x. Papa Pid works when the angles are different. Is sine squared of 2x. Then sine squared, we want to do power reducing on sine. Remember, the price of reducing the power is to double the angle. So we got to make sure we double the angle. So cosine 1 minus, or sorry, sine 1 minus cosine of 2 times the original angle over 2. And then that was over 4. So it doesn't look so bad. Let's go back up here. I don't want to write that division by 4. Let's go as a 1/4 out front. That looks better. So then when we plug in, we have this 1 over 4 floating here. All right, so we have 1 minus cosine of 4x all over 4. We do have a single power of cosine. I didn't say anything about the angle, so we're good like this. Okay. Keep in mind, do not divide out when something is inside a trig with something that is not inside of trig. All right. Next round is your half angle identities. So half angle identities, again, the price of using these, be mindful, a lot of times when we try to use these, we stick the plus or minus in the front. The plus or minus does not go there every single time. It's going to depend on where the angle is. So for example, if our angle is in quadrant 2, sine of an angle in quadrant 2 is positive because y is positive. Therefore, we would use the positive square root. However, if we were looking for cosine, cosine in quadrant 2 is negative, so we would only use the minus sign. So don't use both. Choose the sign based on the quadrant you're in. All right, simplified exact value of each of the following. So what we want to do is rewrite the given angle as half of a unit circle angle. So sine of pi 8. So what I am thinking in my head is sine of pi 8, as I write cosine, is half of what? Well, half of pi fourths, because top times top, bottom times bottom. That's still pi 8, it's just written a little bit differently. All right, so first thing we need to do is figure out the quadrant it terminates in. Pi 8, it's 1 pi, it terminates in quadrant 1. So when we go to use this half angle, we're going to keep it positive. So our half angle for sine, back up here, sine of angle over 2, or that alpha over 2 could be written as 1/2 times alpha. That's the way I prefer it. We're going to use the positive square root, still subtracting it. So 1 minus cosine of the angle over 2, all under a square root. So 1 minus cosine of pi fourths, all over 2, under a square root. And remember, it's positive because our pi 8 angle is in quadrant 1. All right. Cosine of pi fourths, square root of 2 over 2. So these are going to be your rationalizing overload problems. So we got a whole lot of problems going on. fractions first. So what I'm going to do is create a fraction bar even with my big fraction bar because I need to clear that baby fraction bar. And we're going to multiply by 2 over 2. So we're doing this all up under the square root. So distributing, the 2 goes to the 1 and to this fraction. So that's going to give us 2 times 1 is 2, minus the 2's are going to divide out, so just the square root of 2, over denominators, 2 times 2, 4, all under 1 square root. Square rooting a fraction, remember with square rooting a fraction, you are allowed to square root the numerator and denominator separately. So I'm going to scooch this. Actually, we'll just do that, and then I'll erase this. That way it fits. So I can rewrite that as, think about it as the square root of the top and bottom separately. So 2 minus root 2 under its own square root, and then the denominator, square root of 4, that's 2. So this over 2, which could be written this way, or if you prefer, you could slide that 2 out front as a 1/2. 1/2 of 2 minus root 2 under its own. Either way. Next one. Cosine 7 pi 8ths. So what we're thinking is cosine of 7 pi 8ths is half of what unit circle angle. So I got to keep the 7 pi on the top because it's only a 1. I cut 8 in half, it's 4. So we're doing half of 7 pi 4ths. So here's where we got to be careful. 7 pi 8ths, we got to make sure we know what quadrant it's in. So if you're not sure, numerator is 1 less than the denominator. Remember, when you are 1 less than your denominator, that puts you in quadrant 2. So we are in quadrant 2. In quadrant 2, cosine is less than 0. So we are using the negative in front of our square root. So I got my negative. Cosine always adds with itself. So we're going to go 1 plus cosine 7 pi 4ths. All over 2. All under a square root. Make sure that negative is floating out front. All right, cosine of 7 pi 4ths is square root of 2 over 2. Quadrant 4 is positive. Notice it's very similar looking to the last one we just dealt with. So, same steps. 2's got to go first. So we multiply the 2 times 1. We get 2. 2 times our fraction. Square root of 2 is left. All over 2 times 2, 4. And our large square root with negative floating on the front. All right, separate square roots. 2 plus root 2. All under its own, over the square root of 4, which is 2, with a negative out front. Perfectly fine to write it this way. Or I like the 1/2 better sometimes. I just think this looks a little cleaner. And then 2 plus the root 2 inside a square root. Either one's fine. Right. All right. Sine is negative 2 over 5, and our angle is between pi and 3 pi halves. Find tangent of x, x over 2. So first thing, x over 2, we've got to figure out what quadrant it's in. I know where x is, so we need to check x over 2 because that's what the sine's determined by. So pi, so here's our angle. Pi is less than x, which is less than 3 pi halves. So if x is in between here, if we're trying to figure out where 1/2 x is, simply multiply everything by a half. So we know that half x is going to be between pi half and 3 pi 4. I meant to keep that in pink and I changed color. So between pi half and 3 pi 4ths, if we think quadrant-wise, pi half and 3 pi 4ths is in here, somewhere in here. And in that quadrant, tangent is less than 0. Tangent of an angle is less than 0. So we got to make sure we use the negative for tangent here. All All right, so this is kind of like our twos clues problem. Sine is negative, so we know we were in quadrant 3 because x was in between pi and 3 pi halves. So let me get a picture drawn because the ratio we're given is not a unit circle ratio. So this triangle here is based on x. So for x, here is our angle. Actually, no, we're just going to go with the triangle. That's all we need. Sine is y over r, so I know, whoa, y has to be negative 2. R has to be 5. So x is negative also, so x is going to be the negative square root of r squared minus y squared. So 25 minus 4 is the square root of 21. So x is negative square root 21. That's not a very good 21, but it'll work. All right, so we know all three sides, so now we're gonna go find tangent. Tangent of a half angle. Tangent basically just takes the sines and cosines and puts the cosines over. So tangent has sine on top, so that's why the subtraction is on the top, and cosine on the bottom, that's why the sum is on the bottom. So tangent of x over 2, or 1/2 x, I like the 1/2 x better, equals negative, based on what we already decided, 1 minus cosine over 1 plus cosine, all under its own square root. All right, cosine of x is going to be x over r, so negative square root of 21 over 5. So we've got 1 minus a negative square root of 21 over 5, all over 1 plus a negative square root 21 over 5. Double negative, positive, and then subtraction. So I can go ahead and wipe those to plus signs. So notice it's still that same format where we've got square roots and fractions involved. So we're going to do the fraction first, always. Main division bar, this time what's causing a problem is a 5. So the 5's got to go. So distribute our 5, and we get 5 plus root 21 over, distribute our 5 minus root 21. All right, at this point, we still have a problem in the bottom. So now we're going to use a conjugate form of 1. So like I said, lots and lots of rationalization going on. So conjugate form of 1, because I've got to worry about that square root of 21 in that bottom right there. So 5 plus square root 21, 5 plus square root 21. All right, numerator, notice they're the same. 5 plus square root of 21 squared over, we have difference of squares, 5 times 5, 25. Outside, insides drop, negative times positive, negative. Square root of 21 squared is 21. Oops, don't forget the negative outside. All right, except the tangent ones are the ones that take quite a bit of work. And now we're going up here. All right, so 25 minus 21 is 4. Numerator was 5 plus square root of 21 squared. Whole giant square root, negative outside. All right, remember we can square root the top and bottom separately. So square root of 4 is 2. So I'm going to slide that all the way out front as a 1 over 2. 5 plus the square root of 21 squared, well, that square root undoes the square, so we are left with 5 plus the square root of 21. All right, next one. similar problem. Cosine of alpha is negative 2/3 and alpha is in quadrant 4. Find each of the following. So first thing we need to do is figure out what quadrant, we're doing double angles. I lied. All right, so sine of 2a. So we're going to go look at our double angle identities. So double angle identities, remember, if you forget them, you can use your composite identities from the last section. So those are at the top of the notes here. All right, so cosine of alpha is negative 2/3 and alpha lies in quadrant 4. Well, right there, that's a contradiction because this can't be negative. So we're going to wipe that negative out. It doesn't make sense. Cosine's not negative in quadrant 4. It's got to be positive. So there we go. Problem fixed. All right, so cosine of alpha is 2/3. Theta is in quadrant 4, or alpha is in quadrant 4, so let's draw a picture. I'll put it down here. Right triangle. Okay, cosine x over r, so x is 2, r is 3, so that means y is going to be negative since we're in quadrant 4, r squared minus x squared, square rooted. So y is going to be 9 minus 4, y is the negative square root of 5. All right, we got all three sides. So sine of 2 alpha, using our composite for sine, is 2 sine x, or I guess sine alpha, should keep the angles the same, alpha cosine alpha. Alpha is the little fish. All right, so sine of alpha, based on our triangle down here, sine y over r is going to be negative square root of 5 over 3. So 2 times negative square root of 5 over 3 times cosine of alpha. Cosine of alpha was given as 2/3. So just plug in. And math straight across. So we've got 2 times 2, 4. A negative, so negative 4 square root 5 over 3 times 3, 9. All right, cosine of 2 alpha. Cosine squared alpha minus sine squared alpha. And remember, cosine squared of an angle is the same as saying cosine of said angle quantity squared. They mean the same thing. So if cosine is 2/3, I just take 2/3 and I square it. And then sine of alpha, we just found it, I forgot what it was, negative square root of 5 over 3. So I take negative square root 5 over 3 and I square it as well. All right, top, bottom, bottom for your exponent. So 2 squared, 4 over 3 squared, 9 minus negative squared's positive, square root of 5 squared, 5 over 3 squared, 9. And then 4 minus 5, negative 1 over 9. And then tangent of 2 alpha. Since we've already found sine and cosine of 2 alpha, it doesn't really make sense to go use the double angle for tangent. I know tangent of 2 alpha, using my quotient identity, is sine of 2 alpha over cosine of 2 alpha. So let's just use this one since we already know these values. So sine of 2 alpha from A was negative 4 square root of 5 over 9. And cosine of 2 alpha we just found was negative 1/9. So if we use our keep, change, flip, keep the top, negative 4 square root of 5 over 9, change the multiplication and flip the bottom. 9's drop, 1's is obsolete, negative, it's 2 of them, 4 square root 5. All right. So there's some examples of how you can use this, but be very mindful of the signs. You don't have to worry about it on the double angles, but you have to watch it on those half angle identities. And that's because they involve a square root. That's why we can't figure it out. With the double angles, the sign will take care of itself, but not with the half angles.